only one monosubstitutions and three distribution product. This is found to be so in actual practice. Stability of the molecule. The benzene molecule exhibit unusual stability and resists the formation of addition and oxidation product. This is due to the delocalization of pi electron as explained above. Electrophilic substitution reaction. Benzene undergo a number of electrophilic substitution reactions. This is quite easy to justify as the benzene ring is surrounded by the pi electron cloud above and below the plane of atom. These pi electrons are easily available for attack by electrophilic reagent. Final picture. Stability and resonance energy of delocalization energy. It is clear from the above discussion that benzene does not possess a simple calculus structure, hexagonal ring, having alternate single and double bond. In fact, there are no carbon-carbon double bonds as such in the molecule of benzene. What we have is a structure having cycle cloud of delocalization pi electrons above and below the plane of atoms, which is equivalent to the resonance hybrid of calculus structure. The absence of double bond, whether viewed in terms of delocalization of electron or in terms of a resonance concept, is responsible for the calculus stability of benzene. The difference is an energy between the actual structure and the calculus structure, determined from heat of hydrogenation data, which is known as resonance energy or delocalization energy, gives a measure of the relative stability of benzene. Aromaticity. What is aromaticity? Benzene and other organic compound which resemble it is chemical behavior exhibit certain characteristic property which distinguish them from aliphatic compounds. Such a characteristic property constituent what is known as aromatic character or aromaticity. The important properties that characteristic the aromatic behavior are as follow. Even though their molecule formula suggests a high degree of unsaturation, yet they resist the addition reaction generally undergoes by unsaturated aliphatic compound. On the other hand, they readily undergo electrophilic substitution reaction. Their molecule exhibit unusual stability as shown by their low heat of hydrogenation and low heat of combustion. They are cyclic compound generally containing 5 or 6 member ring. The ring present in the air molecule are flat or nearly so. It may be noted that initially aromaticity was thought to be associated only with benzene and other compound containing one or more benzene ring, but later on many heterocyclo compound and other cyclic compound not containing benzene type ring were also found to show aromaticity. Theoretical requirement of aromatic character. Huckel rules. Different theories have been put forward from time to time explain the aromatic character of benzenoid and may other cyclic compound. We will now take up Huckel's 4n plus 2 pi rule to explain aromaticity. Huckel's 4n plus 2 pi rule on the basis of theoretical calculation based upon molecular orbital treatment of monocyclic aromatic compound. Erich Huckel gave the most satisfactory explanation of aromaticity. This is known as 4n plus 2 pi rule. According to this rule, a compound must fulfill the following requirements in order to have aromatic character. It must have a planar or nearly planar ring having cyclic cloud of delocalization pi electron above and below the plane of entire ring. The pi electron cloud in the molecule must contain a total of 4n plus 2 pi electron where n can be 0 onward. In the light of above considerations, it is apparent that an aromatic compound need not necessarily contain a benzene ring. In fact, all that it requires is the presence of flat ring. Benzenoid or not, with 4n plus 2 pi electron in the form of cyclic electron cloud above and below the plane of the ring. The following cyclic system affords some example of structure which fulfill the plane mentioned above condition and are found to exhibit aromatic character. Monocyclic system. Benzene 4 pi electron, pyridine, pyrrole, furane, thiophenone, 6 pi electron in all these aromatic heterocyclics. It may be seen that the hydrogen atom in pyridine is part of a double bond and therefore contributes only 1 pi electron to the aromatic 6 atom, but the hydrogen atom is in the pyrrole is not a part of double bond. This hydrogen atom contribute 2 pi electron to the aromatic sextet. Similarly, in furane, the and thiophene, the oxygen atom and the sulfur atom contribute 2 pi electron respectively. Just as the presence of pi electron cloud in benzene is depicted in a general way by representing is it as benzene, the aromatic heterocyclic compound are represented in a similar way as shown below. Pyridine, pyrrole, furane, thiophene. It may be noted that in furane and thiophene, the oxygen atom and the sulfur atom contribute one pair of electrons respectively to the pi electron cloud, while one pair of electrons remaining with the oxygen or sulfur as a lone pair of electron. 2. Polycyclic system. Huckel rule was developed essentially for monocyclic system and is not applicable to all the polycyclic compounds. Some of the examples where this rule is applicable are given below. Aromatic ions. It is interesting to find that apart from natural molecule, there are certain cyclic ions which show unusual stability of the type associated with aromatic compound. Examination for their structures show that they have also follows Huckel rule, which explain their aromatic character. A few such ions are represented below: cyclopropenyl cation, cyclopentadienyl anion, cycloheptatrienyl cation. In cyclopropenyl cation, the carbon bearing the positive charge does not contribute any electron to the pi electron cloud. As a result, the pi electron cloud contains only 2 electrons delocalized over 3 carbon atoms as shown below. Accordingly, cyclopropenyl cation may be represented as 1,3-di-N propyl cyclopropenyl cation. Offered another example of an aromatic ion having 2 pi electron, cycloheptatrienyl cation or tropylium ion contains 6 pi electron delocalized over 7 carbon atoms as represented below. Here also the carbon bearing the positive charge does not contribute any electron to the pi electron cloud. In case of cyclopentadienyl anion, the carbon bearing the negative charge contributing 2 electrons, while the remaining 4 carbon contribute 1 electron each to the pi electron cloud, so that 6 pi electron are delocalized over 5 carbon. Cyclocatrienyl dianion and cyclonone tetraenyl anion are example of aromatic ion containing 10 pi electron. It may be noted that in contrast to cyclopentadienyl anion, the corresponding cation and the free radical do not exhibit aromaticity as they do not fulfill Huckel rule as shown below. Cyclopentadienyl cation, cyclopentadienyl radical. Having studied theoretical requirement of aromaticity, it can be easily seen that benzene is a perfect aromatic compound as it has 6 pi electron over a flat hexagonal ring, since the regular hexagonal angle is exactly the same as that of sp2 hybridized orbital. There is no angle strain at all in the molecule. In case of other flat ring of smaller or bigger size than benzene, there is always some angle strain which adversely affect the aromatic stability. Thank you.